Okay, so let's try an example. Let's see if we can find a power series solution to y prime minus 2y is 0. What's the solution to y prime minus 2y is 0?
E to the 2x.
E to the 2x. If it doesn't work on this, it ain't going to work on anything, right? So I think I need to what? So the approach to these is not actually super duper hard. It's look at your differential equation, think to yourself, I would like to use a power series. So I'm going to take a power series and guess. I'm going to do this one about 0. In other words, since they didn't tell me that I had to do this around x is 3, I'm just going to do a Maclaurin series instead of a Taylor series because duh, right? Like why make more work for yourself if you don't have to? So I'm going to think that my y looks like the sum from n is 0 to infinity of an times x minus 0 to the n. Okay, and if that's the solution that you're proposing, what should you do?
So, just when you say about 0, you mean x naught, right?
Yeah, I'm saying x naught equals 0. Okay, so if somebody gives you a solution, or gives you a guess, right? Like when we guess for variation of parameters, y equals mu times y homogeneous, what do you do? Yeah, differentiate the crap, cram it back in the differential equation, see if you can force it to work, right? Same thing here. Differentiate this crap. And this is one of those interchange of limits things that I told you was a little bit wobbly. Yeah, so just do it on this one.
Okay.
So this really should, by all rights, be d dx of the sum from n is 0 to infinity of an x to the n, which I am telling you you are allowed to say is the sum from n is 0 to infinity of d dx applied to an x to the n. Right? If you're interchanging limits, yeah, get a mathematician to bless you or whatever. Okay. So when you differentiate this, what do you get? Okay, so you get the sum from n is 0 to infinity, right, of n an
X.
x to the n minus 1. Guys all good with this? Okay, so then I should take that and this other thing and that deal. Like take your parts,
Multiply the first one by 2.
put them together. Yeah, so I'm going to need to multiply the first one by 2, right? You guys see that? Please, whatever you do, don't start writing the sums out. Right? That's the hardest part here, but just don't. Resist the urge to use ellipses in these. It's not a good idea. This is also why I'm doing the simple version. Because if we had a function that was more complicated than 2, I would have to express that also as a Taylor series or a Maclaurin series, and then multiply 2 Maclaurin series together, just like a megafoil, right? Which would be a massive mess, but that's also the thing that computers are really, really good at, right? So over here, you take your bits, plug them together. So I think I got the sum from n is 0 to infinity of n an x to the n minus 1 minus 2 times the sum from n is 0 to infinity of, what goes here?
An x to the n.
An x to the n, and this is supposed to equal 0.
Are you gonna factor the sum thing out?
Am I gonna factor the sum thing out? What do you mean?
The n equals 0 to n equals infinity, are you gonna factor that out or something?
No, my goal is gonna be to stick those together and make one power series.
Mm.
You guys see that? If I could make one power series, maybe I could notice the power series for something I know. That's cool, huh? So, dump all this stuff, because now we need a trick. Okay. So, first things first, look at that, think to yourself, can I combine those? One is
Say
nodding
no.
vigorously. Everyone else is like, huh?
Go for it.
So you could say, all right, so this is the sum from n is 0 to infinity of n a(n) x to the n minus 1 minus 2 a(n) x to the n equals 0. Right? Which is a fundamentally horrible thing. Don't do this.
See, that's what I was asking.
Oh, yeah, so
I was just like, I said it pretty well.
Yeah, you, so I know now what you were thinking.
Yeah.
Let me yell at you briefly, in a very friendly way. This sum is what is this thing? Yeah, this thing's like an operation that you're doing, right? It's not a symbol you can factor. It's like an integral sign, but it is linear, right? So it feels a little bit like factoring, but what you're doing is exploiting linearity of the sum. What is a good idea is to notice like, these x's and those x's could go together, right? Like they're both x's, except that these ones are to the wrong power to stick them together with those ones. You guys see that? So that feels like, oh, if only I had done this kind of better, I could just stick those things together and then I wouldn't have this headache.
Yeah, you could start going from n equals 1.
Yeah, so maybe if I fiddled around with where they start and stop, I could get this to work. So let me take this thing, and I'm going to bring it over here, and I'm going to reconsider it with a different sum. So I'm going to index the first one, instead of by n's, I'm going to index it with k's. So all I'm doing is changing the dummy variable in the first one. So n's a k, n's now ak, x is to the k minus 1 instead of the n minus 1. You see that? And the reason I'm doing this is that I'm going to do something really screwy here in a second. And then I've got my second sum that's minus 2, sum from n is 0 to infinity of an x to the n. This is supposed to equal 0. All good with this? Okay. Screwy bit. If I consider this one, and I said don't use ellipses, but I'm going to use ellipses just for a second to illustrate something. This guy at k is 0 is zero. And then at k is 1.
AK times K.
So at k is 1, it's 1 times a1. So that's a1. And then x to the 0. So that's just a1. That's with me? And then at k is, so that was k is 0, k is 1, k is 2. At k is 2, I have 2 a2x. You guys with me on that? And then kind of so forth, right? Do I need this first term? No? So instead I could really start this sum at k equals 1. Guys with me on that? And then I can make a substitution. So I want to let n equal k minus 1. Because I really would rather have an x to the n there, so that I could put those things together. See that? So if I let if I let n be k minus 1, then I have the sum from infinity minus 1 is still infinity. And when k is 1, n is 0. Just help me out a little bit with this guy.
N plus 1.
K is n plus 1, right? This is a little bit like u substitution, except you don't have the du, right? And then your a sub n plus 1,
X to the
and you have an x to the n. You guys with me?
Minus 2 times.
And then I have minus 2 times the sum from n is 0 to infinity of an, x to the n is 0.
Now you go back to your
Now I can stick these together. You see that? So now if I stick them together, I have the sum from n equals 0 to infinity. Good. That with you guys? No?
You can put those together now just because they both have x to the n.
Yeah, so now I'm kind of, I could put them together before, it just wasn't doing me any good. Right, so here when I put these together, I have n plus 1 times an plus 1 minus 2an
times x to the n
times x to the n
equals 0.
is 0. You guys see that? Okay, and that feels just a tiny little bit screwy, right? Why does this feel a little screwy?
You're just kind of pulling the k out of thin air.
Yeah, I kind of pulled the k out of thin air and then got rid of it, right? So that's a pretty common trick for indexing. You can, if you're a total badass, do that with ellipses, but man, is it hard. I've seen a couple students be able to pull it off. I'm personally not one of them. So I'd either reindex and then combine. What I was really hoping to get at is this thing at the end is a bit wonky. Because this feels like I should be solving for x, right? You see that? Like if I think about this, let me ellipses that thing out for a sec. So if I ellipses that thing out a bit, when n is 0, what do you got there?
A1.
I think I got 1, a1, minus 2, a0, times
1.
x to the 0 is 1, plus, right, so this whole business is the n equals 0 term. Then I have plus, and when n is 1, what do you get? You got 2a2 minus 2a1 times x. That's the n is 1 term. Then you got plus 3a3 minus 2a2 times x squared. So that's my n is 3 term. But not it is 3. Don't forget, Joe. N is 2. Then I got my plus 4a4 minus 2a3 x cubed. You guys all kind of with me? And then I promise this is the last one I'm going to do. So that's going to be a 5a5 minus 2a4 x to the fourth plus some more stuff, right? So that was my n is 3, this was n is 4, and so forth, right? And on the other side, what do you have? 0, right? So all this junk added together is supposed to be 0. Wait a second. That feels like I'm solving for x, doesn't it? Basically, I have a really big-ass polynomial over here set equal to 0 on this side. Right? So if I told you that you were dealing with 1 plus 2x plus 3x squared equals 0, what would you go to do? Yeah, you'd like factor this or quadratic formula this crap or something, right? But you have more x's, right? You have lots more x's. What's the thing you're hunting for, though? Are you hunting for x's? No, hell no. You don't care about the roots either. No. Yeah, you're after y, right? You were after the solution, not after the x's. You don't care when it works. You want it to work all the time. You guys see that? So what are you after? What else is in here? A's. If you knew what the a's are, you could plug them back in over here, and then you'd know what y is. You guys see that? So this isn't a thing about x's. This is one of these guys. I want this to always be 0, right? When is this thing always 0? Well, this one never is. But this one's 0 all the time when all the coefficients are 0. Right? This is me thinking, okay, you've got two polynomials that are equal to each other. One over here, that's all this gobbledygook with a's in it, and this other polynomial that's 0 plus 0x plus 0x squared plus 0x cubed plus 0x to the fourth, right? Plus dot, dot, dot. And now I'm equating coefficients like I do when I'm doing partial fraction decomposition. Right? I want these two things to be identical as functions. You guys see that? So it's slightly screwy, twist of viewpoint. Like you need these to be equal as functions. You're solving for the a's. So a1 minus 2a0 has to be 0. So you get a whole bunch of equations out of this. You get a1 minus 2a0 is 0. What was a0? From the Taylor's, like back in the original Taylor series thought?
Well,
Remember I had this little guy above it? A0 is really f at x naught, right? In my case, that's going to be f at 0, or naming my functions correctly should really be y at 0. That's your initial condition. You're not going to know that, right? I didn't give you an initial condition in the problem, so I don't know the initial condition. But I can solve for all the others in terms of that. Because here, this equation will tell me what a1 is in terms of a0s. Okay, see that? So I just add 2a0 to the other side, divide by 2, you get a1, really the thing I'm looking for, is 2 times a0, right?
So you put 2 times y0.
Yeah, and really, that's 2 times y. Perfect. Nice. And then what's your second coefficient tell you? Yeah, that says 2a2 minus 2a1 has to also be 0.
So it's the same thing?
Well,
Because you have to divide by 2 right there, right?
yeah, so that tells you A2, oops, sorry, writing organization is crucial. That tells you A2 is A1, right? And what was A1?
2y.
A1 was 2A0. And I'm going to leave them as A0s. And then you go to the next one. Right? And the next one says, okay, so 3a3 minus 2a2 is 0. So that would tell you a3 is 2/3 a2, right? But a2 was a1. So that's 2/3 of a1, which is 2/3 of 2a0. With me? Okay. Next thing, right? So your next one is going to be this guy. So you got 4a4 minus 2a3 is 0. So that's going to tell you a4 is a3 over 2. And then you're going to be like, oh, hey, wait, I know what a3 was. a3 was 4 over 3a0, right? So that's 2/3 a0. It's a half of 4/3 of a0. And you can kind of continue on in this rigmarole, right? But in the end, what you're doing is you're collecting the answer about what your y was. So like so far, I know that y is a0, which I didn't necessarily know. That's my initial condition, right? Plus a1 was 2a0. Plus, next one's 4/3 a0. Did I dork one? Oh, duh, x's.
So it's 2 times 3/3 plus 2 times 2/3 plus 2 times 1/3, right?
See, so my next one was, so my next one was,
I thought we had two A0s.
the dork one? Oh, I missed one. That's why it's so
Yeah,
weird.
we had two times A0s.
Thank you. So I had a0 was a0, right? And then a1 should be the coefficient on x. So I have 2a0. And then a2 is also 2a0. That's what got me. And then a3 is 4/3 x cubed.
And
Oh my god. I'm so excited and I'm just doing such a bad job. Thank you. And the next one is 2/3 a0 x to the 4th. And you guys probably aren't quite seeing the pattern, right? Plus da da da. So if I suspected this was e to the 2x, right? I'd be like, okay, so maybe times a constant, right? But let me just do e to the 2x. So e to the x would be 1 plus whatever squared over 2 plus whatever cubed over 3 factorial plus whatever to the 4th over 4 factorial, and kind of so on. You guys see that? Okay, well, this should go in here. So that should be 1 plus 2x plus 2x squared over 2 plus 2x cubed over 3 plus 2x to the 4th over 4 factorial.
then those are all divided by an extra 2? I'm a little confused.
Oh,
Isn't 2x cubed 2x times, or 2, the third 8x cubed?
oh, it totally is. Where'd the extra 2 go?
I don't know.
there's a 3 factorial on the bottom, right?
Oh, it's 3 times 2 times 1. I
So
was
that's
thinking
3
just-
times 2. So
Oh,
this is 8
it's
over
not
3
good.
times 2 is 4/3.
Yeah, that was really tripping me up. I was like, what the hell?
So this illustrates the absolute hardest part about these. You will get to the end, right? And you will be like, okay, I have a power series. What the hell is that the power series of? You guys see that? Like, that is literally the hard part in these problems is, okay, I got to the end, and how do I see the function? So my advice to you would be to try to, if the signs alternate a whole bunch, especially if they do it in patterns of boop, boop, doop, doop, boop, boop, doop, doop, right? If they go plus, plus, minus, minus, or minus, minus, plus, plus, collect the odds and collect the evens separately. Okay, because you don't know something that goes in a 4 pattern. But you do know something that goes in a 2 pattern and something else that goes in a 2 pattern, one that happens with the evens and one that happens with the odds. What are those?
Sine and cosine.
Sine and cosine, right? So sometimes you can collect them and see a sine and a cosine. If you have all positive terms and all the terms are there, try to see the factorials on the bottom. So what I would have done with this one is I would have thought to myself, okay, so y is maybe, let me get the factorial on the bottom here. So I need to see a 0 factorial there. Okay, I already see a 0 factorial there, fine. This guy, I should see a 1 factorial on the bottom. You got that? Yep, there's a 1 factorial on the bottom. Right? Okay. This dude.
2 factorial.
Yeah, let's see. I need a 2 factorial on the bottom, right?
So it'd be like 4 divided by
So,
2 factorial.
Yeah, so to get a 2 factorial down here, right, I need an extra 2 up top. So I think I got 4x squared a0 over 2 factorial to get that factorial on the bottom. So to get a 3 factorial on the bottom here, I got a 3 on the bottom already.
You need a 2 factorial.
So I need a 2, right? So I do, okay, so that's 8 over 3 factorial. And I got a x cubed and an a naught. And then on your next one, you should see a 4 factorial, right? So I've got a 3. But I'm like, okay, so I need a 4 and a 2. So I need a 4 and a, oh, screw it, it's an 8, right? So there's my, I got a 16x to the 4th and a 4 factorial on the bottom and an a naught. And you could keep playing that game. So that's kind of how you would see an E. Okay? Otherwise, another totally reasonable thing to do, especially if you're actually doing an engineering problem this way, get your power series, plug it in a computer and see if the graph looks familiar. Right? If it looks like something near 0, it could well be that thing. If it looks like some function you know, take that function you know, throw a couple parameters in there, differentiate the thing a bunch of times, right? Like make the Taylor polynomial and see if you can make them the same. Cool with that? It's a little reverse engineering trick I only learned the hard way. Cool. Questions there? At the end though, if you can't get the like, okay, and this is obviously the power series of something, I'm okay with that. If you leave it as some recursive relationship, that's totally fine. Sometimes you'll have to.